Hi, welcome to the next video. So let's continue where we left off. Now I want to talk about properties of the integral, of the definite integral. So let's start with that. Properties of the definite integral. Properties of the definite integral. So last time we talked about two different ways to calculate a definite integral, and this class now we're talking about properties. Okay, so one property is if you take the definite integral from a to b of f of x dx, that's equal to the negative of the definite integral from b to a of f of x dx. Also, the integral from a to a of f of x dx is 0. Okay? So those are two properties of the definite integral. Okay, I'm also now going to put a list of 8 more properties. And so to do that, I'm going to erase these two equations. And I'm going to erase the title. Okay, so I'm still talking about properties of the definite integral. But I need to give myself more space on the board for this list. Okay, so I'm going to suppose all integrals exist. Okay, and the first property is that the integral from a to b of c dx is equal to c times b minus a, where c is any constant. So I'm going to try to have 2 columns here maybe. So definitely from a to b of c dx equals c times b minus a, where c is any constant. It's a constant. 2. Definitely from a to b of f of x plus g of x dx is equal to the sum of these two separate integrals. Okay? So the definite integral from a to b of f of x plus g of x dx is the integral of f of x dx plus the integral of g of x dx from a to b. 3. The definite integral from a to b of c times f of x dx is equal to c times the definite integral from a to b of f of x dx, where again c is any constant. C is a constant, any constant. Okay, so c constant for short for c is any constant. 4. The definite integral from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x dx. This integral from a to b of g of x dx. That's 4. 5. The definite integral from a to c of f of x dx is equal to the definite integral from a to b of f of x dx plus the integral from b to c of f of x dx. Okay, so those are 5 properties. Okay, so these are going to be over here. I'm going to put the comparison properties of the definite integral. Comparison properties of the integral. So this is going to be property 6 in this list. If f of x is greater than or equal to 0 for a less than or equal to x less than or equal to b, then the definite integral from a to b of f of x dx is greater than or equal to 0. Okay, so if you have a non-negative function, non-negative means greater than or equal to 0. If you have a non-negative function, little f, on this interval, then when you integrate over that interval of f, you get a non-negative number. The definite integral is greater than or equal to 0. 7. If f of x is greater than or equal to g of x for a less than or equal to x less than or equal to b, then the definite integral from a to b of f of x dx is greater or equal to the difference from a to b of g of x dx. And then 8, I'm going to put here. I'll put 8 here so it's lines. Okay. So number 8, if little m is less or equal to f of x less or equal to capital M, for a less or equal to x less or equal to b, then little m times b minus a is less or equal to the definition from a to b of f of x dx, which is less or equal to capital M times b minus a. Okay, so these are 8 properties of the definite integral. 1 through 5, and then 6 through 8 are comparison properties of the definite integral, of the integral. Okay, so I'll leave this on here for a short time so you can copy this all down. You can always pause the video and go back if you need to. Okay, so these are 8 properties. Okay, so if you use these correctly, you can deduce more with these 8 properties. But you have to use them correctly. If you don't use them correctly, you can reach the wrong conclusions, right? Okay, so in 7, f of x is greater than g of x, right? In 8, f of x is sandwiched between little m and capital M on this interval. And what that means, if you integrate over that interval of f, then it's going to be little m times b minus a is less or equal to that number, and this number is less or equal to capital M times b minus a. All right? Okay, so a picture to illustrate 8 would be this. Here's the x-axis, here's the y-axis. Let's say this is f. Let's say that's f. Let's say this is the interval from a to b. Okay. Well, little m, let's say little m is this. Okay, so little m is a number that's less than or equal to the height of this graph f of x from a to b. Okay, let's say capital M is the height of the function at its highest point, which it would be here. Let's call this number capital M. And what it's saying is that the area, this integral here, is the area under this curve from a to b, right? I could shade it in, that's the area, right? Now, if you look at this rectangle here, oh, no, not there, here, this shaded area. This is the rectangle whose base is b minus a, and whose height is little m. So the area of that rectangle is little m times b minus a, and if you can see the area under this curve, the area under this curve takes up more space than that rectangle. So this definite integral is definitely greater or equal to the area of that rectangle. Right? And if you look at capital M here, now let's look at the area of this rectangle. Now, remember that rectangle. Now let's say we take the area of this rectangle, where the base is b minus a and the height is capital M. The b minus a times capital M is the height of this larger rectangle. And so the area of this larger rectangle not only contains the area into the curve, but it contains the area of extra space. And so capital M times b minus a has to be greater or equal to the area under that curve, or that definition. Okay, so you see how this picture, the area of this smaller rectangle and the area of this larger rectangle, illustrate how this definite integral is sandwiched between little m times b minus a and capital M times b minus a. Right, the area of the smaller rectangle, or this, is less or equal to that, which is less or equal to capital M times b minus a. Okay, so this is a picture illustrating the proof of 8. Okay, so these are 8 properties of a definite integral. So let's keep going. Let's keep going. Example. Use properties of the integral to evaluate the definite integral from 0 to 1 of 4 plus 3x squared dx. And so use properties of the integral to evaluate definite from 0 to 1 of 4 plus 3x squared dx. Let's do that. So the definite from 0 to 1 of 4 plus 3x squared dx. Okay, so we use the properties of the integral. And by properties of the integral, you can actually focus on just properties 1 through 5. Okay, so using properties 1 through 5, we're going to calculate that definite integral. So this is equal to the definite integral from 0 to 1 of 4 dx plus the definite integral from 0 to 1 of 3x squared dx, right? So here we're adding 4 plus 3x squared, and so you can separate them into two separate definite integrals. Okay, I can take the constant. I can take the constant and move it outside of that integral. So this is the same as definite from 0 to 1 of 4 dx plus, and we'll move the 3 outside of it, 3 times definite from 0 to 1 of x squared dx. Okay, and now the next one is the definite from 0 to 1 of a constant, right? Is that constant times the difference from the upper limit and the lower limit. So this is 4 times 1 minus 0. Okay, so the value of that definite integral is 4 times 1 minus 0. See, the circles are corresponding with what I'm doing here. Plus 3 times that definite integral. Okay, so plus 3 times this definite integral. The value of that definite integral is 1/3. Okay, that's 1/3. Okay, so we can just go with that. Okay, so then this is equal to 4 times 1, which is 4, plus 3 times 1/3, which is 1. So this is 4 plus 1, which equals 5. And so the value of that definite integral is 5. Okay, so that's one example. Another example is if definite integral from 0 to 10 of f of x dx is 17, and definite integral from 0 to 8 of f of x dx is 12. Find definite integral from 8 to 10 of f of x dx. Okay, so let's use one of the properties of definite integral. That is specifically property 5. Okay, so by property 5, we can say the definite integral, I'm afraid, maybe this is a solution. Definite integral from 0 to 10 of f of x dx is equal to the definite integral from 0 to 8 of f of x dx plus the definite integral from 8 to 10 of f of x dx. That's by property 5. Okay, just label that equal sign as 5. So that's by property 5. And so that implies, I'm going to use the implication symbol there. That means if this is true, then what I'm about to write is true. This definite integral is 17. So that 17 is equal to this integral, which is 12, plus that definite integral, which is definite from 8 to 10 of f of x dx. And so from this equation from property 5, that implies, plugging in the values of this definite integral and that one, that implies that 17 is equals to 12 plus that definite integral. And so that implies that that definite integral, right, knowing how to subtract, definite integral from 8 to 10 of f of x dx is equal to 5. Right? 12 plus 5 is 17. Okay, that's the answer. Find that definite integral, and we found it right here. It's equal to 5. So in both cases, the answer is 5. All right, and so that ends section 4.2. So let's continue to 4.3. Okay, so 4.3, evaluating definite integrals. So 4.3, evaluating definite integrals. Okay, so evaluation theorem. Evaluation theorem. If f is continuous, so if f is continuous on the interval a comma b, the interval a comma b, then the definite interval from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime is equal to little f. Okay, so remember in 3.7, we learned that a function has many antiderivatives. In fact, it could have infinitely many. It usually has infinitely many antiderivatives. The evaluation theorem is saying you can choose any antiderivative of a function, little f, and you can evaluate the definite interval from a to b of f of x dx as being equal to capital F of b minus capital F of a for any of those infinitely many antiderivatives. You choose any one, and you'll get the same number for that difference, and it's equal to that definite interval. But again, f has to be continuous on that finite closed interval a comma b. Okay, so you have to make sure you meet these conditions in order to apply the evaluation theorem. But if you do, then you get that result. And so this is a very fast way of computing a definite interval. You don't have to use, well, I did the entire board of space calculating a limit. You can just use the evaluation theorem to do it. Okay? So let's look at an example. So the definite interval from 0 to 1 of x squared dx. Okay, right on the earlier, this was part of the solution where I plugged in that was 1/3. So now let's use the evaluation theorem and let's get that this integral is 1/3. Let's do it very quickly. So this is going to equal, well, the evaluation theorem says if you have a continuous function f on a closed interval, right? That's the conditions of this theorem. Here in this example, we're going to let f of x equal to x squared on the interval finite closed interval 0, 1. That f is continuous on that finite closed interval. If you were to graph it, you would see the graph you can draw without lifting your hand. That's not a proof that a function is continuous, but it's just a fast way to intuitively see that a function is continuous. You can draw that graph without lifting your hand from 0 to 1. Okay, y equals x squared. It looks like that, and you can draw it without lifting your hand. Okay, so we have a continuous function on a finite closed interval. And so that meets the conditions of the evaluation theorem. And so the conclusion then is that the definite interval of it from 0 to 1 is equal to capital F of 1 minus capital F of 0, because 1 is the upper limit and b and 0 is the lower limit of that definite interval. And here capital F is any antiderivative of that little f. So we need an antiderivative of this function little f. Well, how about capital F of x equals 1/3 x cubed, right? So you need to be able to find an antiderivative of a function. And so 3.7 is where we did that. So capital F of x is equal to 1/3 x cubed. If you take the derivative of capital F of x here, right, you get 1/3 times 3, which is 1, times x to the 3 minus 1 power, which is 2. So capital F prime of x is x squared, and that's the f of x. So capital F is an antiderivative. This capital F is an antiderivative of that little f. And so you can use that one for capital F. So you have 1/3 times 1 cubed minus 1/3 times 0 cubed. And so that's equal to 1/3 minus 0, which is 1/3. And so here, before when we used that was equal to 1/3, this is showing you that using the evaluation theorem. Okay? A fast notation for doing the same thing would be to say that the differential from 0 to 1 of x squared x cubed is equal to 1/3 x cubed evaluated from this vertical line, 0 to 1. And what this notation is saying is that you're taking this function and you're saying you're plugging this number into that expression for x minus this expression when you plug in that number. That's 1/3. That's the same answer. So here, instead of writing all this, instead of writing capital F of 1 minus capital F of 0, or capital F is equal to 1/3 x cubed, you can shorten all of that by just writing that this is equal to that antiderivative, which is specifically 1/3 x cubed, vertical line, which says vertical line, lower limit here, upper limit there. And the meaning of this notation is you plug in this number for that expression and subtract plugging this number in for that expression. Okay? Right? So notation, the notation again I'm using here, I'm going to make a point of this so that you know to use it, because when I was learning calculus I didn't use this notation and it took me a while to understand what the evaluation theorem meant, and this notation makes it much easier to understand. So if you have capital X evaluated from 0 to 1, that means it's that function plugging in 1 minus that function plugging in 0. Okay? So that notation means that. And I'm applying it here. Now instead of writing the function, you can write the expression. So in this case, instead of capital F of x, I write 1/3 x cubed, valued from 0 to 1 is 1/3 1 cubed minus 1/3 0 cubed. Just 1/3. Okay? So you use this notation. When calculating differentials, it's much easier. Okay? In words, again, what this equation is saying is the definite integral from 0 to 1 of x cubed dx is equal to 1/3 x cubed evaluated from 0 to 1. Let me say it slower. The definite integral from 0 to 1 of x squared dx is equal to 1/3 x cubed evaluated from 0 to 1. In words, that's how you would say that in words, and this is how you would write it quickly using that notation. Okay? Two different ways. You could say it out loud, you can write it down. Okay? Okay, so this is an example of calculating this definite integral using the evaluation theorem. Let's do another example. Okay, so the definite integral from -1 to 2 of x to the 4th dx. So let's examples calculate this one. All right, well, an antiderivative of x to the 4th is 1/5 x to the 5th. And then evaluate it from -1 to 2. So quickly, that can be done. And so then that's equal to this expression, plugging in 2, minus that expression, plugging in -1. And so this is making it much faster calculating the definite integral, right? And so 1/5 times 2 to the 5th, 2 to the 5th is 32, so that's 32 over 5. Minus -1 to the 5th is -1. -1 times -1/5 is positive 1/5, so that's plus 1/5. That's 33 over 5. And that's the same as 8.6. Okay? Oh, not 8.6. That's 6.6. Okay, 6.6. As a fraction in the simplest form is 33 over 5, as a decimal it's 6.6. Okay, so here we use the evaluation theorem. I'm going to put a star here and label this. The star is just to explain that problem, so maybe you could also think of the stars. That's important. Two purposes that star has. Okay, so let's look at another example. And so we're still going to use the evaluation. It's definitely better than using the limit. Don't you know this? A common question people ask is, well, if the evaluation theorem is so much easier than the limit, why do you have the limit in the first place? And so the reason is that the limit is actually the definition of the definite integral, right? Without the limit, we wouldn't have we would have no definition of what the definite integral is. And so the evaluation theorem is a consequence of the definition of a definite integral. Okay? The evaluation theorem is a theorem that says, given the definition of a definite integral, given that you know what a definite integral is, you can say that that is equal to what the theorem says. Okay? So the evaluation theorem is deduced as a result of the definition of the definite integral. Okay, so both are needed. All right.